All right, let's talk about linear approximations. And here's the key. So if we look at the example that we just did, the example of that elliptic paraboloid. So here's a little sketch of it. We had this elliptic paraboloid, and we found the equation of the tangent plane. The equation of the tangent plane was z equals 4, excuse me, it was z equals 4x plus 2y minus 3. What we're saying is that when x comma y is close to 1 comma 1, so this is what we're saying. When x, y is close to 1 comma 1, in fact, we can just use this approximation. It's approximately 1 comma 1. F of xy is approximately 4x plus 2y minus 3. Right, that's what it means to say that the surface is getting very flat and resembling the tangent plane as we zoom in. So this is called linearization, right? So this would be the linearization of our elliptic paraboloid. And we're saying that this is a good approximation to f of xy when xy is near 1 comma 1. This part is key when x comma y is near 1 comma 1, because if your point x comma y is far from 1 comma 1, then just looking at the graph, we no longer have a reason to suspect that the values are close to the values on the plane, right? You see that? So that's not close at all. Whereas if we are in here, then that's really close. So that's a good approximation. Okay. So let's look at some formalization of this. So this is the linear approximation, aka the tangent plane approximation of f at 1 comma 1. So this is only valid when x comma y is near 1 comma 1. So let's use it to approximate what is f of 1.1 comma 0.95. Okay, well, so we'll say f of 1.1. Let's actually do this. So we say that we know that when x comma y is close to 1 comma 1, f of x comma y is approximately L of xy. Okay, and we know that L of xy is equal in this case to 4x plus 2y minus 3. So we're concerned for x is 1.1 and y is 0.95. So then that means that f of 1.1 comma 0.95 is going to be approximately 4 times 1.1 plus 2 times 0.95 minus 3. Okay, and that we can easily do. Let's see, with a calculator, that'll be 4.4. 4 times 1.1 minus 2 times 0.95. Sorry, plus. I don't know why I want to turn that into a minus. And now minus 3. So get about 3.3. So f of 1.1 comma 0.95 is approximately 3.3. Now, that was very easy to compute. Let's see, since we do have a formula, what is f of 1.1, 0.95 exactly? So our formula for f of x, remember, was f of x comma y equals 2x squared plus y squared, right? So now it would be 2 times 1.1 squared plus 0.95 squared. Okay, so 2 times 1.1 squared plus 0.95 squared. And that's 3.3225. So our approximation isn't that bad because that is actually very close to 3.3 is very close to 3.3225. Okay. All right. Now, just as a reminder, if you take a point that is not close to 1, 1, like 2, 3 is not that close, then your approximation suffers. So, right, so f of 2, 3 is equal to 17, but the linear approximation at 2, 3 is equal to 11. Not as good of an approximation. Okay. All right. So in general, we have this formula here for the equation of the tangent plane. The only thing that we've done differently is, remember before we had z minus z naught equals fx, right, of AB. Or actually before we had x naught, y naught, and then x minus x naught plus fy, x naught, y naught, times y minus y naught. So the only thing we've done is we've changed the x naught with a, and we've changed the y naught with b, and then z is now f of a comma b, z naught. And so we just added plus z naught to both sides. Okay, so we get z is equal to all that stuff. Okay, so this equation is exactly the same. And we are saying that this is the formula for the linearization of f at the point a comma b. So this is definitely a formula you want to have on your cheat sheet for the exam, and you want to have an example showing how to use it. So this is the linearization of f at a comma b. Now, making the approximation, saying that f of x comma y is approximately this, is called the linear approximation, right? And it's only valid if your partials are continuous. So let's look at what happens if your partials aren't continuous at that point. Remember, we had this example. This was an example we went over in class, where our equation f of xy was xy over x squared plus y squared if xy is not at the origin, and then 0 if it is at the origin. And remember that we said that we had a ridge, I think we had a ridge of 0 here and 0 as you approach along the y-axis. But if you approach along the y equals x line, then you're stuck at 1/2. I think that was what happened. So it turns out that the partial derivatives exist at the origin, right? So the partial derivatives exist as you're approaching from the x-axis and the y-axis. Partials are actually equal to 0, but those partials are not continuous. Okay, so since the partials are equal to 0, what would our linearization be? It's supposed to, at the origin, so at the origin, let's go to our formula here. The linearization of f at 0, 0 would be, so we need f of 0, 0 plus fx of 0, 0 times x minus x naught plus fy at 0, 0 times y minus y naught. And so what is f of 0, 0? It's equal to 0. So that's going to be equal to 0. And fx, we're saying that's equal to 0. That's an exercise. right? Maybe we'll assign that for homework. And fy is equal to 0. So everything multiplies out is just going to be L of xy equals 0. Now, what does this plane look like? This plane is the plane z equals 0, which is just the xy plane. Okay? So what we're saying is that the linear approximation would be f of xy is approximately equal to 0. That's our L of xy. Okay? But we've got a whole bunch of points that are 1/2. Any points that's along that line y equals x. So f of xy is not going to be a good approximation to the linearization since the partials aren't continuous. Okay. So what we do is we give the definition of a function being differentiable. A function of two variables is differentiable if the partials are continuous, because that means that we can approximate the function as we can have a good linear approximation of the function. Okay. So recall that for a function of one variable, we define the increment of y as delta y equals f of x a plus delta x minus f of a. So here was the picture for that. So say this is your function f of x, and you're at some point a. Now, this let's zoom in here. Okay, so this value here is going to be f of a. And now if this is a, and we have now here a plus delta x, right? So delta x, so this distance is delta x. Then this would be f of a plus delta x. And the increment in y is the distance, is f of a plus delta x minus f of a. Okay, so that is delta y. Okay, so what we're going to do is we're going to have this have an analogous definition for functions of two or more variables. Okay, so we said that if a function, this was back in chapter 3 with one variable, if a function is differentiable at a, then delta y, which is that increment, is equal to f prime of a times the increment in x plus something that goes to 0 as delta x goes to 0. Okay. So we're going to extend that for our definition of a function being differentiable if it's of two variables. So we're looking at that increment in delta z. That is going to be the difference between f of a comma b and f of a plus delta x comma b plus delta y. Okay, so that's our increment. And if this increment is of the form the partial of f with respect to x times the increment in x plus the partial with respect to y times the increment in y plus epsilon 1 times the increment of x plus epsilon 2 times the increment of y, and we need for both of these to go to 0 as those increments go to 0, then we can say that our function is differentiable at the point a comma b. Okay? So the result of that is going to tell us that as you let epsilon 1 and epsilon 2 go to 0, then that means that these are going to 0. So that means that this increment is approximately equal to this part right here, right? And that allows us to use the linear approximation as a good approximation, right, for when x comma y is near a comma b. Because that will, x comma y is near a comma b, means that these increments here are small. And if these are small and this is going to 0, then this increment is going to be really small. But remember, this increment is f of x comma y minus f of, this increment is f of a comma b minus f of, I'm doing it backwards, sorry, f of a plus delta x comma b plus delta y minus f of a comma b. Right, so it's the change in the z value when you change x, the x coordinate and the y coordinate, right? And if this is really small, then that means that these are really close to each other. Okay, so that's what we're doing with this linear approximation. So again, sometimes it's difficult to use that definition because it involves epsilons, epsilon 1 and epsilon 2. So the easier way, and or one easy way to check for differentiability, and the way that we'll be doing it, is to just look to see if our derivative, our partials, are continuous at the point. So this is a theorem, is that if the partial derivatives exist near AB and are continuous at AB, then f is differentiable at AB. And that means that we're able to know that f of x will be approximately equal to its linearization near AB. So let's do an example just to solidify these ideas. We're supposed to show that f of xy equals x, each of the xy is differentiable at 0, 1. So let's do that first. So we want to show that it is differentiable at 1, 0. Okay, so now the way we're going to show it's differentiable is we're going to use theorem 8. So we're going to find those partials, show that they exist near 1, 0, and show that they are continuous at 1, 0. So I need the partial with respect to x of f. Now let's see here. F, just so I don't confuse myself, f of xy is equal to x times e to the xy. Okay, so now if I'm taking the partial with respect to x, now remember y is a constant, so I'm going to need to use the product rule. So I've got x times e to the xy. So I want the derivative of x, that's going to be 1, times e to the xy, plus x times, now I need the partial of e to the xy with respect to x, that's going to be y e to the xy. Okay, so I get e to the xy plus xy e to the xy. And that's the same as 1 plus xy times e to the xy. And now let's do similar computations for the partial with respect to y of f. So this, now remember, now x is a constant, so the x stays the same, right? That's just a constant. And now the partial of e to the xy with respect to y, I'll have another factor of x and then just e to the xy. Okay, so that one was actually easier. So now these partials are continuous everywhere, right? We're not dividing by 0. We don't have any. They're continuous on their domain. So these partials are definitely continuous near at 0, 1, and they're defined near 0, 1. So by theorem 8, f of xy is differentiable at 0, 1. Okay, let's find this linearization. Now, the formula for the linearization is going to be z minus z naught equals We need the partial at 1 comma 0 times x minus 1 plus the partial with respect to y at 1 comma 0 times y minus 0. Now, how do I find my z naught? That's going to be f of xy. So f of 1 comma 0. What is f of 1 comma 0? So x is 1, y is 0. So that's just going to be 1 times e to the 0. So that'll just be 1. Okay. So this is going to be 1. And now I need the partial with respect to x. So the partial with respect to x at 1 comma 0 is going to be, thank you, 1 plus 0 times e to the 0. So that's going to be 1. And I'm also going to need the partial of f with respect to y at 1 comma 0. And that's going to be 1 squared times e to the 0, which is equal to 1. Okay, so everything is just 1. So this will be 1. And this coefficient will be 1. So we'll get z equals 1 plus x minus 1 plus y. So it's just z equals x plus y. So that's our linearization. So let's put here L of xy. That's our linearization. And now we're supposed to use it to approximate f of 1.1 comma negative 0.1. Okay, so f of 1.1 comma negative 0.1 is going to be approximately L of 1.1 comma negative 0.1 since f is differentiable at the point 1 comma 0. Okay, and 1 comma 0 is really close to 1.1 comma negative 0.1. So our linearization is just x plus y. So this is just going to be equal to 1.1 plus negative 0.1 equal to 1. So f of 1.1 comma negative 0.1 is approximately 1. All right. The next topic we'll talk about is the topic of differentials.